Hello, everyone. Today we're going to start the next unit, organic chemistry, and this is the final unit in the chemistry curriculum. So we're going to start off with a little introduction. So first, before we get into anything, let's talk about these terms and what they mean. So organic chemistry, what is it? Organic chemistry is the study of organic compounds. That's not a really good definition because we're using the term in the definition. So what are organic compounds? Those are compounds that contain carbon, but it can't just contain carbon. This is how the Regents will often define it. So that's your number one element that's in the compound, but it can't just contain carbon. It has to also contain carbon. It has to also contain hydrogen. So it must contain carbon-hydrogen bonds. So it's not just carbon, it's got to contain carbon-hydrogen bonds. So hydrogen is also going to be present in the compound, but the Regents will just define it specifically as it must contain carbon. So you got to know how to take it one step further and realize it needs those carbon-hydrogen bonds. So what do I mean by that? Well, we're going to learn how to draw some of these formulas today, both the molecular and what we call the structural. So let's look at an example like this. Let's say I have this, and these lines represent bonds, right? Think back to our bonding unit when we drew covalent compounds. So let's say I draw this. Those are my hydrogens. So this we call a structural formula because it actually shows us the structure. It shows us how the molecule is going to look. Now we also need to be able to express it like this. If I just write C2H5OH, now that doesn't show me the structure. So all we call this is the molecular formula. And we've done this before. So both of these are different ways to express the formula. This gives us a little bit more information. It shows us the structure, but they both show us the number of atoms of each element that make up the molecule. So we're dealing with covalent compounds here. So we're dealing with molecules. So all these organic compounds are covalent. So we're dealing with molecules. So you're going to see those terms coming up again. So now organic compounds is a big category. So a lot of things fall into the category of organic compounds. So what if you're not an organic compound? So remember, just containing carbon isn't enough. So something like CO2 or any ionic compound, like if I have sodium carbonate or even H2O. So like even though CO2 contains carbon and H2O contains hydrogen, they're not organic because they don't have the required carbon-hydrogen bonds. So we got to have carbon, and we also have to have carbon-hydrogen bonds. So if you're not organic, we call these inorganic. So that's another big category in chemistry, but we're not going to talk about that here. Everything we're going to talk about is dealing with our organic compounds. So we're going to start off really simple, talking about just a certain type of organic compound called hydrocarbons. So it has the word hydro and carbon in it because these are molecules that contain only carbon and hydrogen. So they just contain two elements. But if you look at the numbers of each you can have, the different bond formations, and there's a lot of different possibilities. So there's a lot of different compounds just containing these two elements, carbon and hydrogen. All right. So before we get into that, let's just look at some of our general properties. So remember, there are always exceptions to these generalizations, and we'll go through those as required throughout the unit. So first thing is that they're poor conductors of electricity. So let's remember why. We're dealing with covalent compounds. We have sharing of electrons, so there's no charge formation taking place. So we do not have free-moving charged particles. So remember, that's our requirement for conducting electricity. We need free-moving charged particles. So with covalent compounds, there are no charged particles. So they're insoluble in water because they're generally non-polar molecules. So remember when we talked about this, we had that term like dissolves like, meaning polar substances dissolve in other polar substances and nonpolar substances only dissolve in other nonpolar substances. So water, remember, is polar. So a lot of our organic compounds are going to be nonpolar, so they don't dissolve in water. So they tend to have low melting and boiling points because, again, remember, if we're dealing with nonpolar molecules, those tend to have weak attractions between molecules. If you would think back to our intermolecular forces, our symmetrical nonpolar molecules have weak attractions between them because there are no poles pulling them together, no opposites attracting, right? So they have slow reaction rates because often we're dealing with large molecules, and remember how that affects your rate of reaction. Big molecules takes a long time because you have a lot of bonds and you got to break those bonds down. All right. So these are all kind of things we've talked about throughout the year that are just coming into play now. So back to specific hydrocarbons. So what is a homologous series? So homologous series are molecules with similar structures and properties. So homo means same. So we're dealing with molecules in a group that have similar structures and properties. So sometimes they call these families, right? So it's similar. They're not exactly the same. So just like you and your family members, you might be similar, but you're not exactly the same. So it's the same thing here. So let's go through the types of hydrocarbons that we're going to be dealing with, the different groups, our three series or families. The three groups here that we're going to be looking at are the alkanes, the alkenes, and the alkynes. So again, they look very similar. There's really only three letters differentiating between them: A, E, and Y. So these are your alkanes, alkenes, and alkynes. So what the difference is the types of carbon bonds. The alkanes have all single bonds between the carbons. The alkenes have one double bond between the carbons. And the alkynes have one triple bond between the carbons. So let's draw some examples of these. So let's say I have an alkane. So we'll do a 3-carbon chain. 1, 2, 3. And we'll put our H's all around. So that's a 3-carbon alkane, all single bonds between the carbons. Now, when we talk about the general formula, this is a formula where all of the hydrocarbons in that same series are going to fit in with this general formula. So for the alkanes, it's CnH2n plus 2. Now, N, think of N meaning number. N is the number of carbons in the compound. So CnH2n plus 2. So in this case, my N, how many carbons are in this compound? There are 3. So it's C3. And now take that 3. So it's simple algebra. We plug that in, right? 2 times 3 is 6 plus 2 is 8. So the formula is C3H8. And now that should be in line with what we just drew. So look, we got 3 carbons. Now if we count our H's, is 3, 6, 7, 8, right? So it should always match up. So now the N, when that changes, that's going to change your number of H's. So it should change it accordingly and still be in line with whatever you draw. So if there were 4 carbons, then that would mean we would have 10 H's. So if we drew that, it would look like that. And we'll get to that later when we go through it. So the next one is the alkenes. So now these have a double bond. So when we draw this, here's my double bond. But now understand what that does. Remember, carbon can only form 4 bonds. So when I have a double bond here, that's now taking away two hydrogens that could have been bonded to this compound, right? So look at how this up here compares to this down here. By me forming a double bond here, look, I lost these two carbons, right? So now we would call that an alkene because we have our double bond there. But now how does that affect our general formula? We lost two H's. So take away two H's. Our general formula is simply CnH2n. So does that match up, right? So it's C3H, 2 times 3 is 6. And if we count, we have 6 H's. That's it. And the last one is an alkyne. So now instead of a double bond, we've got a triple bond. And now we got to put our H's all around, but remember, each carbon can only form 4 bonds. So look, this one's 1, 2, 3, 4. That one's done. Put our H over here. 1, 2, 3, 4. So it looks kind of weird because it doesn't seem like we have enough H's because this triple bond is taking away all those possible H's because each carbon can only form 4 bonds, right? So now look what happened. We lost 2 more H's. So my general formula is just 2n minus 2 now. So that would be C3H. 2 times 3 is 6 minus 2 is 4. So it's now C3H4. And if we count 1, 2, 3, 4, right? The general formula should always work out, right? So whatever formula you draw, it should be in line with the general formula for that hydrocarbon series. So notice what happened. I went from 2n plus 2 to H2n because we lost 2 hydrogens when we form that double bond. And then when we form that triple bond, we lose another 2 hydrogens. And now it's 2n minus 2. Okay? So you don't have to memorize this. It's on your reference table. So it's on table Q. So take a look at table Q here, and it shows you the names, anes, alkenes, and alkynes, says what N is, the number of carbons, gives you the general formulas, and it even gives us some examples, and it draws them. So here's your single bonds, double bonds, triple bonds, right? Now it's between the carbons. So the single, double, and triple bond are always going to be between the carbons. So that's an important part here. It can't just be between anybody. It's got to be between 2 carbons in the compound. So now the last thing before we get into drawing different types and how to name these and how to draw them is 2 more terms, saturated and unsaturated. So saturated compounds contain only single bonds between the carbon. So just like when we did a saturated solution back in the solutions unit, remember what a saturated solution was. It was full. It was maxed out. It couldn't hold any more solute. So you can think of a saturated compound as full of hydrogens. It can't hold any more hydrogens. So that's another way to kind of look at it. So it's all single bonds between the carbons. Unsaturated compound contains a double or a triple bond between the carbons. So that's not full of H's, right? It's unsaturated. It's not full of hydrogens. It can hold more because we could potentially break these double or triple bonds and add in more hydrogens. So alkanes, they're full. So we would call those saturated. So write that in on your table here. The alkenes and the alkynes we call unsaturated because they can hold more H's. We can break these double bonds and triple bonds and add in more hydrogen. So they're not full. So they're unsaturated. Just like an unsaturated solution is not full of solute, we can add more. We can add more hydrogens to an unsaturated hydrocarbon. So now how do we name these? It's really, really pretty simple. So use prefix to show the length of the carbon chain. And how do we know these prefixes? It's on your reference tables, table P. So take a look at your reference tables. P is right above Q that we were just talking about. Here it is. So these prefixes, they come in front of the name and they tell us exactly how many carbons are in the compound. So you always have this resource available. It's in your reference tables. So you're going to be using that a lot here. And then we use the appropriate ending to show the type of bonds. So for that, we're going to use good old table Q. And we'll see how that works out as we go through this. So let's look at some examples. So I'm going to try my best to draw these here on this. So let's say I have let me start off with this. We'll put our H's in. Make sure you draw the H's, get in the habit of doing that, and make sure they're capital, right? Don't draw lower cases. We're going to draw capital here. So that's one. Let me draw a couple of examples here. Copy these down as we go. Okay, so here are 3 examples. So now let's go through our steps. Pretty simple. So step 1, use the prefix to show length. So let's count our carbons. 1, 2, 3, 4, 5. So there's 5 carbons. So when you look on table P, your prefix for 5 carbons is pent. All right. And then the last part is we use table Q to get our appropriate ending. So we say, all right, is it an alkane, an alkene, or an alkyne? So this has all single bonds between the carbons. So this is an alkane. So it ends in ane, pentane. That's simple. All right. So this is pentane. Done. So now let's again think about our general formula. So the alkanes are CnH2n plus 2. So if this has 5 carbons, that means my N is 5. So 2N plus 2, my H must be 12. So if I count my H's, I'll see there are 12 of them. And that should always match up. It's a good way to check to make sure you're doing things correctly. So the next one, we've got 4 carbons. So 4 carbons is bute. All right, not but. It's bute. It's got a double bond here, which means it's an alkene, so it ends in ene. So this is called butene. That's simple. Prefix for the number of carbons, ending for the type of hydrocarbon that it is. Alkenes end in ane, alkenes end in ene. I'm sure you could guess what alkynes end in. So again, let's look at our general formula here. For the alkenes, it's CnH2n. So bute 4, right? If my N is 4, then 2N is 8. And I do have 8 H's. All right, and the last one, we've got 1, 2, 3, 4, 5, 6. So that's hex. And it's got a triple bond. So we know it's an alkyne. So those end in ine. So this would be called hexine. Done. And then again, our general formula, CnH2n minus 2. So hex is 6. So that's C6. And then H10. 2 times 6 minus 2 is 10. And there are 10 H's. Go around and count. There's 10 H's. So pretty simple. Prefix, number of carbons, ending for the appropriate group that we're dealing with, the appropriate family. So alkanes end in ane, alkenes end in ene, and alkynes end in ine. So now what about going the other way? So if you want to draw the hydrocarbons, so let's go through our rules here. So we want to use the prefix to draw the carbon chain. So that prefix is going to tell us how many carbons are in the chain, and then we'll place the double or triple bond in its proper location. But that's only if a double or triple bond is present. If it's an alkane, there is no double or triple bond, so you don't need to do anything. And then we use the hydrocarbons to give each carbon 4 bonds, right? Remember, carbon has 4 valence electrons, so it needs to form 4 bonds to fill its valence shell. Each bond gains an electron in that shared pair. So carbon's always got to form 4 bonds. So you want to make sure every carbon has 4 bonds in your final molecule that you're drawing. So again, let's do some examples here. So I want to draw butane, and then I want to draw propene, and then I want to draw pentine. So let's go and draw these. So pretty simple. Bute, we look on table P and we see what bute is. That's 4. So first thing we do is we draw 4 carbons. Then the next thing, what did we say step 2 was? Place a double triple bond if necessary. We don't have that here because it's an alkane. There are no double or triple bonds. And then use hydrogens to make sure each carbon has 4 bonds. So we got to add in our bonds and draw in our hydrogens to make sure each carbon has 4 bonds. All right, so we're good. So 1, 2, 3, 4. Go around and check. Does every carbon have 4 bonds? And it does. All right, and again, let's make sure it fits in with our general formula. So remember, alkanes are CnH2n plus 2. So that means this is C4. So my H has to be 10. And it is. 10 H's, we're all good. All right? So the other thing I want you to be aware of that you might see drawn here is something called the condensed structural formula. So you might see something called the condensed structural formula drawn here, which is exactly what it sounds like. They're condensing it. They're making it smaller by pulling in all the H's and just drawing them next to the carbon and then using a subscript to show you how many there are. So like for this, it would be CH3 for the 3 hydrogens, and then the next carbon only has 2 H's. So does the next carbon. And then the last one again has 3 H's. So this is what we call the condensed structural formula. All right, so be aware of this, that it exists and what it means, but never draw this. Okay, you'll only always have to draw this. So you don't have to draw this, but sometimes it's shown to you, so just understand what that means, but you'll never have to draw it. All right, so next up, propene. So prop, it's 3 carbons. So we look on table P, 1, 2, 3. And now ene tells me there's a double bond. So where the double bond goes or the triple bond can change, but for now, we're just going to put it between the first 2 carbons. So there it is right there. And then fill in with H's. So make sure you're not overdoing it. So count your hydrogens. So I already have 2 bonds. 1, 2. I only need 2 more to get me to 4 for that carbon. This carbon already has 3 bonds, so I only need 1 more H to get me to 4 bonds. It's easy to overdo it and start throwing H's down here. And then this last carbon has 1 bond, so I need 3 more H's. All right, so that's propene. So again, remember our general formula, CnH2n. So 3 carbons, so my N is 3. So my H has to be 6, 2N, and it is 1, 2, 3, 4, 5, 6. And now, remember, you don't have to draw the condensed structure, but understand what it looks like. So it would look like CH2. So we've got 3 carbons still, but now we're just using these subscripts to show us how many H's there are. And the last one, pentine. So pent, look on table P, or we know from math or what we've done in the past with our naming compounds, pent is 5. So 1, 2, 3, 4, 5. Right? Now the YNE, the ine, tells me it's an alkyne, so it has a triple bond. So for now, just put that multiple bond between the first 2 carbons, and now go in and fill in with our H's. So this first carbon only needs 1 H because it already has 3 bonds here. So we can only have 4. This guy doesn't need any. 1, 2, 3, here he has 4 bonds. The next one, we need 2 more to get me to 4. Same thing on the next one here. 2 more to get me to 4. And then the last one needs 3 more bonds. So we add in our H's. And we're good. So now, what would my general formula look like? CnH2n minus 2, which would be, so my N, pent, is 5. So my H has to be 2 times 5 minus 2 is 8. If we count, it's good. So that's a good way to check and see, did you screw up and put too many H's or not enough? Does your general formula match up with the actual number of H's in your compound? And if so, you're good. So now again, what does the condensed structural formula look like? So this one would be CH, and then just C, and then the next one CH2, CH2, CH3. So remember, you never have to draw the condensed structural, but what you want to be able to do is understand what it's showing you, and then also realize, look up here, all these H's, when you have a double or a triple bond, you're kind of losing H's. So you can see that like drop in H's. So realize there's a multiple bond there somewhere. So that's all I really want you to be able to do with that. So that's pretty much it for this lesson. I'll see you all next time.